Hi everyone, so I'm Klaas de Jonge from Ghent University, and today I will present a set of indicators we developed or we puzzled together for smart ventilation systems. The main reference for this presentation is my own PhD, which I presented last year, and more specifically chapter 6 of this work, where I looked at expanding existing frameworks for performance assessment of smart ventilation systems that focused typically on comfort and energy performance, and trying to expand that with the health aspect of IAQ. To start this investigation, I started from the concept of desired indoor air quality, and this phrasing I found very interesting, and it's part of the AIVC definition of smart ventilation. So they have this whole definition, and there they say, well, a system should be able to provide desired indoor air quality. And what's interesting there in this phrasing, that it's not the minimum indoor air quality, also not the maximum indoor air quality. So there's kind of an ambiguity, which is interesting, because if you say, well, if you have a definition of desired indoor air quality, you could say that the goal of any ventilation system is to provide and maintain the desired air quality to the occupants. But also, if a system succeeds in this endeavor, you could say that, well, with regards to IQ, we can say it's a good system. It's not perfect, not the best system, or not the most optimized, but it's a good system. There's no real faults in this. And based on that idea, I ended up with the question, well, if you can define desired air quality and you look at performance of a system, well, that it means that the performance of a smart ventilation system should, as it provides desired air quality, it means that it's defined a sort of boundary box, the absolute limits in between which the performance should lie. So if the air quality is within this boundary, that's the point where you can look at other things like non-IAQ costs, which is, for instance, energy use or relative performance. So you have this absolute boundary, and applying this idea, I ended up with a quite straightforward method of two-phase performance assessment. So first phase is pass-fail. So meaning that you check if a certain condition is met, and all conditions should be met in order to even look at the relative performance. And I ended up with a set of indicators, and the concept of a set here is very important in the sense that we picked and selected and put together them in such a way that a downside of one metric can be captured by another. So it's never a good idea to just delete one of these and move along, because then you're probably overseeing something. So in this way, we really wanted to have a holistic vision on indoor air, on the performance of a smart ventilation system. Now, in interest of time, I don't have the time to go through all of these, so I'm selecting a couple of these, which I think are valuable to share with you today. So of course, big part of the work was adding health. Let's start with two health indicators, and let's take one small step back and look at, well, what are the health effects you can actually expect from indoor air quality? And you can quite easily categorize them in two categories. So there is short-term health effects, which are very fast and negative, of course, physiological reactions. So imagine you enter a space and after 15 minutes you have a headache because of high concentrations. You're working at home, you're in a space for 4 hours, but after a while you feel drowsiness, which is linked to a certain VOC which is present. So these are very fast reactions, and you could quite easily say, well, if you have a ventilation system in your home with normal sources, you should never go above these limits. So in that sense, the desired air quality is very straightforward. It's just don't go beyond these limits. And there are existing frameworks for this. So there is an American IAGL limits, but also in the European context, there are these kinds of exposure limits. So that's the desired indoor air quality. For the long-term health effects then, it's a bit more nuanced in the sense that it's more of a effect of prolonged exposure, which is based on epidemiological research. And there it's actually the link between a dose of exposure and a certain health outcome that they found statistically. But the end so they found that there are health effects based on dose. Because of that, there are also chronic guideline values available. So for most pollutants, you'll find that there are chronic guideline values, but these are actually not in place to define a sort of desired indoor air quality. They are in place to make sure that in the end, the dose is low, and then finally the impact on the population is also low. Here we propose to not use the long-term health effects in the IAQ checklist or in the hard limits, but actually move it to the relative metrics and introduce a harm metric directly as part of the indicators. And the harm metric that we propose is the disability adjusted life years, or DALYs for short. And it's a way to quantify what the impact of certain illnesses and a certain exposure is on the health of a population. Small example, we know that exposure to PM 2.5 or increasing exposure increases the amount of cases of chronic bronchitis. So we know there's more people with that health outcome. We also know that people with chronic bronchitis, well, on average, they will not live until their full life expectancy, but also during their lifetime, they will not be able to participate in active sports, for instance. So that means that if you have an exposure concentration profile of a person or of a population, you can estimate the DALYs. There is more detail to this method, of course, for which I would love to refer you all to a paper we published 2 years ago in Indoor Air. Because of course I want to have some more time for some more indicators, and the next two I want to give a bit more detail about are the ones focusing on comfort. Now these are not new in a sense that I think they're quite well known, but we took a different spin on it, let's say, because after thinking it through and puzzling in developing this set of indicators, we actually ended up that it's quite easily to describe both comfort in terms of relative humidity and comfort in terms of bioeffluence, or as you want, CO2 produced by people, to describe it in a way as what is now the desired indoor air quality. And now you could say, well, for relative humidity, you want your ventilation system to keep exposures within these limits most of the time. And if you put a percentage on that, well, let's say most of the time is 90% of the time at home. Well, you end up with not a relative metric, but rather a desired IAQ definition, and thus this relative humidity as part of the IAQ checklists. The same reasoning you can apply to the bioeffluence. So you could say, well, again, on well-known methods, on PMV, PPD approaches, well, let's just say that on average, only more than 80% of people should feel comfortable, and to limit peak exposure, let's say, well, only 5% of the time, more than 50% of people may experience discomfort. So you have the definition of a range, and thus actually not using it as a relative metric, but rather as a pass-fail IAQ checklist. And that's a bit of a different spin than we actually thought we would end up with. But again, in the set of indicators, we really feel that this makes sense. Then finally, I want to explain one last indicator, namely the health equivalent energy efficiency. Now, this one is a bit more tricky to explain, so I'm going to first show some results. And these are results of a simulation study of 8 smart ventilation systems. We also did 6 reference continuous ventilation systems, and for each of those systems we did 10 households. So it's a relatively big set of simulations which resulted, of which we analyzed the results. And with regards to health, we needed to, of course, add certain unhealthy pollutants, and after literature review, we selected 5 volatile organic compounds for this study. For the IQ checklist, I can be quite brief actually, because of the ones I presented today. All of the systems were able to keep the concentration levels below the short-term health effect limits. All of the systems were able to keep the perceived comfort within the defined range, but none of the systems was able to actually keep the relative humidity discomfort within the predefined range. If we then move over to the relative performance metrics, so there's the harm metric, which is now shown on the y-axis, and then there is, of course, the energy use indicator, which is plotted on the x-axis. The black dots on this graph are all the smart ventilation systems, so the performance of those systems. The orange dots are the continuous reference system of an MVHR system. The blue dots are the reference system of the continuous MEV system. What you can see in this graph is that there is actually a trade-off being made between high energy use and harm. So you have these 2 indicators, but they're of conflicting interests. So more energy, less harm. So how to decide which system is actually best for a certain situation? There we found that, well, you can observe a certain trend in the reference systems, namely that they actually follow an exponential decay function. And one thing you need to know for Belgium is that it's obliged to install a ventilation system in a newly built building, but it's not obliged to operate it at 100% of the nominal flow rate. So you, as a user, you can just set it at half of the flow rate or even less. So in practice, you will not always find that if there is a ventilation system installed, that you're at the 100% mark. Actually, all the values on the blue line for an MEV system are possible outcomes of a system you would install, a non-smart system you would install today. So then, with that in mind, you could say, well, but what if I do make that system smart? What is the added benefit of making it smart? What is the added benefit of the better controls in this case for a certain system? And then compare the energy use of the smart system with the reference at equal health, resulting in the health equivalent energy efficiency. Now, this specific methodology was based on an existing one they used for comfort, but also has 2 big downsides. First, it's a very relative scoring. So that means that you can compare smart versions of an MEV system with the MEV system and among each other. But you can't really compare the results of this smart implementation of an MEV system and a smart implementation of an MVHR system. So if the reference changes too much, you can't really compare these values anymore. Another thing that's worth discussing is that this reference line assumes that the nominal system or the nominal system that you select is as you would want it. And for the case of Belgium, well, the nominal systems were defined more than 30 years ago. So you could say maybe an update of the reference system is the least you could do, but maybe it's better to just get rid of the references overall. And that's also what I tried, or that's why there is also another possibility here. So let's, instead of having a system as a reference, just define a certain reference line based on, for example, target values you have for harm, so limiting harm to a certain extent, but also limiting energy use to a certain extent. So this has the added benefit that regardless of the configuration of the sizing of the controls, you have a fixed reference to compare each system to. If you then calculate these results for the different systems, you see that overall and most of the time, the two health equivalent energy efficiency ways of calculating give equal results. So it means that most smart ventilation systems actually are more health equivalent energy efficient than the nominal reference system. But you can also see that, for instance, for system D8, it doesn't, because it was a decentralized system, it didn't really have a fixed reference. So there it was only possible to give it a score based on the fixed reference and not really based on a reference system. So to conclude, so we developed a curated set of indicators, and here the idea of a set is really important because the limitations of one metric can be overcome with another, giving a very holistic view. With regards to health, we propose to have both a harm-based health metric for the long-term health effects, but also definitely check the short-term health effects and making sure that they are not passing certain limits. And that resulted in a framework that actually, if you would start using this to optimize your system, will optimize for health and energy within comfort boundaries and not optimized for comfort boundaries as such. So that's well over my time, so I will go quickly to Baptiste, who will present his work now.